Okay, so the previous screencast that I gave to you guys, I talked about some fairly fundamental simplistic balancing equations and a process that you should use to go about doing that. And 9 times out of 10, it's going to work and you're going to be in great shape. But there are some cases where it doesn't work as well as you would like it to. So I'm going to show you these ones inevitably have to do with combustion of a hydrocarbon, and that's going to make things more difficult for you. So let's take a look at one here. Imagine I have a compound. Actually, let's see. Probably want to give myself a little bit more room here. Oh boy, I guess that won't work. I'm going to lock this out, and it'll give me more room to write. Okay, so I'm going to start with C5, oops, H6, NS, plus oxygen, and this will result in the formation of a whole bunch of things. Carbon dioxide, water, nitrogen dioxide, and sulfur dioxide. Okay, and why don't I go ahead and insert the different states of matter. This is liquid, this will be a gas, and the rest of these things are gases as well. Okay, so let's do what we've done in the past. We need to tally things up to make sure that we have the at least initial amount of things all squared up. So we're going to have carbon, hydrogen, nitrogen, sulfur, and oxygen. And again, it's very important that you look at this and realize that I'm using just those numbers in their elemental form. I'm not putting anything into its diatomic form or anything like that. It's always just singlets of this whole thing. So I can go ahead and copy and paste this right here. Oops, didn't mean that. Paste it right here. I'll just do it sort of midway instead of there. Okay. So let's just take a look at these numbers here. We have associated with carbon, we have 5, 6 hydrogens, 1 nitrogen, 1 sulfur, and 2 oxygens. And over here, it's a little bit more complex. You just have to make sure you don't forget about all the oxygens all over the place. We have 1 carbon. We have 2 hydrogens. The H2 is important to see there. 1 nitrogen, 1 sulfur, and then we have 2 here, 3, 4, 5, 6, 7 oxygens altogether. Alright, so remember how on the last screencast I told you guys to make sure that you look for the thing that's not found in multiple compounds on one side of the equation? Well, I want you to see here that oxygen is found in absolutely all these things. So that's going to make a big hairy mess of things. So I would suggest that you not start off with oxygen, but you start off with something else. And in fact, why don't we go ahead and start off with the carbon, because we can see we have the 1 carbon over here, and we ultimately need to have 5. So let's go ahead and establish the 5 carbons and see where that gets us. So I'm going to go ahead and I'm going to put, let's see, I'll use, what kind of letters? I'm going to use pink to do this. So I'm going to go ahead and at least I'm going to start off putting in 5 for my carbons over here. And I'm going to go through and change these things now. And hold on, let me go back to having a green color. So I don't have just the 1 carbon over here, right? I'm now going to have 5 carbons. So I'll go ahead and put a cross out through that. Oops, that's way too big. Cross it out, and we're going to put 5 here. But of course, now that I've just increased the number of carbons in my carbon dioxide molecule, because I put a coefficient there, I also am going to increase the number of oxygens. And so this becomes now 10 oxygens, 5 times 2, 11, 12, 13, and then lastly 14, 15. So I can put a line through here and write 15 for the number of oxygens. Now, of course, that's great, except that we just now threw our oxygens way out of balance over on this side of things, because on my reactant side here, I only have the 2 oxygens. Well, let's hold off again. I don't want to mess with the oxygens yet, because we know that it's going to get changed as we start to change all the other atoms in this. So let's just tick down here. We have, in this case, over on this side, on my reactant side, right, I have 6 hydrogens. I only have 2 over here. So let's change things around so that we can get 6 hydrogens over on this side. And of course, in order to do that, I would want to put a 3 in front of the water, because 3 times the 2 associated with the subscript of the hydrogen is going to equal 6. So I can go in here, cross out my hydrogen, write 6, and I don't need to change anything on the other side. However, once again, I need to change my oxygens. So I'm not going to have just 15 oxygens anymore, since we can see here I'm going to have the 10 that I had here, 5 times 2, add 3 more, so 13, 14, 15, 16, 17. So now I have 17 oxygens going on over here. Nitrogen and sulfur we don't really have to do anything about, right? Because we have the correct number of nitrogens and the correct number of sulfurs on both sides of the equation. So now if we have everything here, this is okay, this is okay, this is okay, this is okay. The only thing that's not okay is the number of oxygens. I have 17 oxygens on my product side and only 2 oxygens on my reactant side. Now, unfortunately, 17 is a pretty lousy number because it's obviously not an even number. There is no number that I can put in front of here, right, that will lead to 17. That's a whole number. And that's the key, right? Indeed, there is no whole number that I can put there, but I can put a number that is in front of there that would equal 17. And of course, you all know that 17 divided by 2 is, ooh, that's a terrible looking 8. 8.5. Now, you might say to yourself, what? I thought you could only use whole numbers. In fact, that's absolutely true. You can't use anything but whole numbers when you're balancing equations. So what do you need to do? Well, it's a nice, easy fix. You're going to take this entire equation that you've just created here with all these new pink coefficients, and you're going to multiply all the coefficients that exist in each one of the compounds by 2, because that's, you know that if you multiply a number that has a half in it, like 8.5 by 2, it's going to make it a whole number. Now don't forget that in each one of these situations, we assume that there's a 1 in front of anything that doesn't have a coefficient. So that means when you multiply through, when you distribute a 2 throughout this entire equation, it's going to multiply 2 times 1 in those situations. So let me go ahead and select up this equation that I've got going here. I'm going to copy it, and I'm going to paste it on the next page. Okay, there we go. And if I multiply each thing through by 2, then instead of having 1 CH, let me lock this out actually so I can expand and write this small. I'm not going to have 1 CH, a C5H6NS, I'm going to have 2 of those. Oh, bad Chang. I guess I used red. C5H6 and S, and there you go, pink. No, what color am I using? Blue. Okay. All right, and that is liquid plus 2 times 8.5, and that brings us to 17 oxygens, or gas form. And this leads to 2 times 5, or 10 carbon dioxides, gas, plus 2 times 3, 6 waters. I know this is going hideously slowly. I'm sure you get it at this point, but I'm just going to continue. 2 NO2s, also a gas, and then lastly 2 sulfur dioxides, SO2s, like so. Alright, so all I did was multiply everything through by 2, and as long as you multiply both sides of the equation by 2, as you know from algebra, that's not going to change anything. Now, let's just be absolutely sure that we've got this right by doing our check. We're going to take the number of carbons we have, number of hydrogens, number of nitrogens, sulfurs, and oxygens. And I'm going to go ahead and copy and paste this combination right next door. I have the same exact tally going on here. And if we use pink here to write out the numbers, I have 2 times 5 carbons, right? 2 times 5, the coefficient of 2 times the subscript of 5. So that's going to give me 10 carbons over here. And then if I go over to this side, I have my subscript of 1 is assumed for my carbon here. I have a coefficient of 10. So indeed I'm going to have 10 carbons over here. And I don't have carbons in any of the other things that I have over on my product side. So good. We're checked out and set with carbon. Hydrogen. So in hydrogen, I have my 2 as my coefficient, and I have my 6 as my subscript. So 2 times 6 is 12. 12 carbons over hydrogens over here. And if I look at where I have hydrogen, you got it right here. I have 6 times 2 subscript there. So I have the same thing going on here. 12 hydrogens. And then we look at nitrogen next. And in the case of nitrogen, I have only one subscript of a subscript of 1 associated with the nitrogen, but the coefficient's important. So 2 times 1 means that I have 2 nitrogens on this side. And again, if you look over on this situation, you have a coefficient of 2, subscript of 1, so 2 times 1, or 2 on my product side. So again, reactants and products balance out. We have not broken any laws of physics in this process. And then we'll continue the same thing. Sulfur. There's going to be 2 sulfurs because of this coefficient over here. Oxygens. We are going to have 17 times 2, or 34. All right. And let's go over to the product side. Looking at the sulfurs, we have 2 times the 1, assumed 1 that you have over here with the sulfur. So that's going to give us 2. And then let's carefully count up all the oxygens we have here. So we have 10 times 2, right? There's 20. Plus, we have 6 times 1, which is an additional 6. Right? Then we have 2 times the 2 that are here, or 4. And then we have the 2 times the additional 2 here. And again, that's 4. All right? So if we add up 20 plus 6 plus 4 plus 4, lo and behold, surprise, surprise, that is going to equal 34. So there you have it. We've go ahead and we balanced that equation perfectly. And again, this is going to happen when you have combustion equations of certain molecules that exist out there. So tomorrow, folks, in class, we're going to do a problem set in class, and I'm going to have you guys balancing equations, some easier ones, and then we'll lead into some of the more difficult ones like this. Okay, see ya.